Okay, so last time we were in class, we discussed hexokinase. So we started getting into regulation, right? And we said that the points of regulation needed to be where there was the reactions were not at equilibrium. And like we said from the beginning, these are steps 1, 3, and 10, okay, of glycolysis, okay. And we talked about the regulation of hexokinase. Yeah, those are down too. Okay. And so we talked about some ways that hexokinase was regulated. Again, we said hexokinase 4 is found in the liver, where hexokinase 1 can be found in different tissues. Okay. And some of the different ways that hexokinase in the liver is regulated, okay, was that it has a higher KM, so it's responsive to higher glucose concentrations. What's that even mean? You guys remember what KMs are? Higher KM, okay. Remember, this is our enzyme activity. If we look at our maximum enzyme activity, we go over, like for this red line, this is like our maximum enzyme activity. And if we go to half of that and go over, that gives us a value for our KM. So it's what our substrate concentration has to be for our enzyme to be at half of its maximum activity. Okay. So notice the KM for hexokinase 1, right? And there's hexokinase, here's max, is about half. It is really small. And that gives you an idea of how responsive it can be. Like this hexokinase 1, whether you're at 5 millimolar, which is where the blood glucose levels are usually, or you're 10, double that, it's not really responsive, is it? It's just working as fast as it can. It's not responsive because of the isoform we're looking at, okay? Where hexokinase 4, again, if we look at its KM, it's right in that range. Look, it can really adjust activity. It can really adjust its activity. It can slow down if glucose levels are really low, which we would want it to because it's in the liver and it's going to let the brain and the heart get all the glucose. Or we can speed it up if glucose levels get too high, because then we got to help reduce blood glucose levels in the blood. Okay, so that's what's meant by this first. It has a higher KM, so it's responsive to higher glucose concentrations. And remember, that's hexokinase 4 found in the liver. What's the role of the liver? Help us to maintain our blood glucose levels. One of the many roles of the liver. Okay. It's not inhibited by glucose 6-phosphate. Why would hexokinase care about glucose 6-phosphate? What's the relationship between hexokinase and glucose 6-phosphate? Gluconeogenesis, okay. So, but when you think about hexokinase, right? Remember, what does hexokinase do? Here it is right here. Remember, it's this big, huge enzyme. Glucose comes and binds the active site and it gets phosphorylated and you get glucose 6-phosphate. So glucose 6-phosphate is the product of hexokinase, right? We got reactants on the left, products on the right. Glucose 6-phosphate is a product. So what this is saying that glucose 6-phosphate doesn't inhibit the enzyme that catalyzes this reaction, okay? So as it's taking in glucose and phosphorylating it, again, this is our hexokinase in the liver, right? Phosphorylating it keeps it in the cell. That helps reduce glucose in the blood, right? It takes it out of the blood, right? You think about this? Here's our blood. Glucose is getting too high in the blood, right? It enters the cell through these transporters. Hexokinase phosphorylates it. It can't get out. Now, this does not inhibit the enzyme. Thank goodness. Okay, because that means as it's bringing all this glucose into the cell, it can keep operating. Okay, it can keep going. Where we saw glucose 6-phosphate does inhibit other types of hexokinase. Because if that glucose 6-phosphate is not continuing through glycolysis, right? If it's not getting pulled through and being used up, that means like our muscles are not contracting, right? It doesn't have this need for energy. And if it's not, if there's no need for energy and your body's very efficient, it's gonna be like, stop taking the glucose, right? It's gonna inhibit the enzyme and say, slow down. If there's enough of that glucose 6-phosphate around, okay? It's not getting burned up. Okay. And again, the function is to clear blood glucose at higher glucose concentrations and then storm away as glycogen. Okay. All right, so this is what we looked at last Wednesday. Okay, so we started talking about the difference in regulation. I asked you guys to do activity 25. Yes. 25 and 27 are the ones we had today. But 25 is on page 104 and 105 of your workbook. I think it is also on our page. So that's what I want us to be. How many of you guys did it? Oh, it's not in there. Okay, so let's think about maybe 10 minutes to look at that. Okay. Does anybody, like, anyone want to take a picture of my book? Like, you have a question? I don't have a hard copy. Yeah, okay. But I'd rather you have the questions. It'd be cool to not have the questions. I'd rather just take a picture. Okay, anyone else want to take a picture? Because you have a workbook.
I have a workbook.
Yeah, yeah, no, it's just that in case someone doesn't have a workbook, there's nothing on it on our Canvas page. So I just want to make sure you guys have the questions so that I'm not just, you're not. Okay, do you have access to it?
Yes.
Okay.
I don't know what.
Okay, do you want to take a picture?
Yeah.
Picture. So take a picture of this page and this page. Okay. That way when I say, well, what about question 1 or are you? We're on the same page. So you guys can get in like small groups, 2 to 4 people, and think about these questions. They're all about the regulation, and most of them have to do with hexokinase. Okay. We got a test next week. Yeah. Yes.
I was gonna ask a few questions about the test.
Okay.
I'm gonna ask one, do you do more on like information control or like conceptual applications?
Conceptual applications.
Okay, and then is it like choice, random question?
Mix. So some multiple choice and like matching, that we fill in the blank, probably drawing the substrate versus endpoint activity curve.
Yeah.
Mix it up. So you guys start with critical thinking questions. Number 1, right? Define allosteric control of enzyme activity. Okay, and we're looking through questions 1 through 6. Okay, so don't get stuck on like, don't need to read the outline right now. Don't do that.
Oh, so did you? First. And then now it's there, kind of reverse this, it's not taking it out.
Yeah.
Enabling function, the enabling function, it's more like an increase one more times. Ever to and that's like. You can take that.
Okay, no, I just want to. No, since it start at it's 1 through 6, so it's that, the last question here and. Yeah. What do you mean to that?
Oh, yeah.
It's always gone, I hear. Oh my God. I don't know why, I have to download them on my, I don't know why they're popping up. They're not popping up. So I have to, there's certain like. Yeah, I had to download their presentation. Oh, it's working on lot. Try to list the linear one that we're seeing. Okay. I'm not sure how. Yeah. Well, just want to think about it, right? So again, it's not affecting things at like a transcriptional level or translational level. It's not another regulatory protein, right? And so it's a relatively small molecule. And so when I think of like small molecules affecting an enzyme, now we'll see an example of this later today that's controlled by hormones, so we consider it hormonal regulation, but this is a small molecule that's not through the hormone.
Okay, now.
So I consider it like a small molecule affecting activity. I think that's so. I guess that's the fine. Yeah, what? Doing good, okay. I just bought one of these. My daughter was like, yeah, hey, Sienna.
Pretty good.
Yeah, how are you feeling about that? Wait, who's this? I love that. It's in the slide. There's a door. Thank you so much. Let me know it's starting. Okay, go ahead. Okay, and I think
I don't think you're tracking.
But now the people the next set of next, which is fine, but that's what we're going for.
Sorry, I was thinking about. I knew that.
I don't know.
Does anyone want to write their curves for number 2 on the whiteboard, like maybe over here on the side? Anyone want to do that?
So competitive would be, but something else. Combined with- It basically would just like, or maybe it would do something. This, I think, the finance wouldn't be able to- wouldn't be able to- So it's like competition between the two things.
Yeah.
It's fine to go to first.
But if you. Misconception. You go on that one, I think we'll. Let's see what happens when you go on that. Take about another minute, guys. So I did ask, and as some of you, more than raise your hands, actually did do it since last Wednesday. So like I said, we'll go over quickly. I'll put up a key, and then you can take more time on it later too, if you guys want to take more time on it. But again, these exercises are great ways to just really think about the stuff that comes out of your class. Lisa, you still have another minute or so.
Okay, 3. Talks about why exoplanets forward is how it is.
You guys, let's look at this question together. So the first one says define allosteric control of enzyme activity. So what do you guys put? What do you guys think? What do you guys think of allosteric control?
You wrote that it was like how the concentration of a substrate affects the enzyme activity.
So that's true, the concentration of a substrate can affect the enzyme activity, that's absolutely true. But when we talk about allosteric control,
Binding to an enzyme.
that's a very important component. Yeah, so, and just to add to that, it's a small molecule, okay? So it's a small molecule, okay, that binds somewhere else besides the active site, okay? And we're gonna see a great example when we start to look at the next regulation, the phosphofructose one. We have to have some great slides for that. I don't have slides for that for hexokinase, okay? But a small molecule binds an enzyme, and remember, an enzyme is a huge molecule. In fact, let's just go to that picture, right? Here's PFK1. They're not even showing you all the atoms, right? They draw it like this, right? But you can kind of see like these are carbon, 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 you know, these are the different side chains. But it's huge, right? This is a representation of the enzyme, right? It's all these amino acids come together. Now, for hexokinase, we can get, well, so allosteric control, a small molecule binds somewhere that's not the active site, okay? And can either inhibit it or activate it, okay? Hold on a second, okay? Can inhibit it or activate it.
So just like an on-off switch, that's what allosteric control is.
Yeah, but it's again, it's an important component, small molecule binding somewhere besides the active site. Right, to either activate or inhibit an enzyme activity. Okay, small molecule binding somewhere besides the active site. Okay. And so that's what glucose 6-phosphate can do, okay? And yeah, sometimes it might change the activity of the enzyme from a hyperbolic curve to a sigmoidal curve. Okay, it can affect the Vmax, right? How much activity the enzyme can have. Okay, so that's allosteric control of enzyme activity. And it's a small molecule, it binds elsewhere from the active site, and then it can either inhibit or activate that enzyme. Okay. Questions on that? Okay, so number 2 says translate the information provided in this activity into 2 line graphs of V velocity versus glucose concentration for both hexokinase and its isozyme glucokinase, also known as hexokinase 4. Okay, on the same plot. For simplicity, we're going to assume the same Vmax for both enzymes. Okay, so include curves for each enzyme in the presence and absence of glucose 6-phosphate. What type of inhibition might you expect? Okay, so let's see. So Jacob was nice enough to put his curves up on the board over here. I don't know if you guys, like Layla, can you see that? Oh, you can. All right, great. I'm just always worried about that column right there. Okay, and there was some information given to you on that first page, right? It tells you that characteristics of hexokinase in most cells and characteristics of hexokinase in the liver cells called glucokinase. And it tells you that there's a sigmoidal concentration dependence on glucose for glucokinase. So yeah, so Jacob's representing that here, right? It's a sigmoidal kind of shape there. I might just make this a little bit more like that. Not that I'm being picky there, right? But just, yeah.
It seems like from the graph for Vmax.
Right, so the Vmax are different, right? And so, and I know because I'm here, this looks very similar to this, right? But if we were gonna make them the same, we might have this, it said for simplicity, make them the same, even though they're not in real life. But if we were gonna make them the same, right, we would bring this one all the way up to there. That would be the difference, right? So that makes the Vmax the same, okay? Okay. So again, we've seen that hexokinase in muscles and other cells react to smaller concentrations of glucose, where glucokinase in the liver takes a little bit more glucose to get it activated. Okay, now, in the presence of glucose 6-phosphate, your glucokinase looks very similar to the one you had here, right? So that was, Jacob had that, I messed up his curve, so, but right, glucokinase is not inhibited by glucose 6-phosphate, where hexokinase is, okay? So hexokinase, remember, this is in the muscle. This is your liver. Okay. And remember, G6P is the product of hexokinase. Okay. So what type of inhibition would you expect from glucose 6-phosphate? What do you guys expect?
Allosteric.
Yeah, allosteric, right? It's a small molecule. It's probably going to bind somewhere else on the enzyme and cause it to be inhibited. Okay. Yeah. Yeah. You want me to fix that first?
And also, HK1, in the presence of G6P, its Vmax never recovers, no matter how much glucose we have, right?
Right. Yeah, because think about why is glucose 6-phosphate? So if you're in the muscle, right?
Like even if there's a lot of glucose in the blood, muscles can do it.
No.
They don't.
Because they don't care about the glucose in the blood, right? That's not their rule. Yeah.
And
Okay. Yeah, if we go back to the hexokinase 1 is not sensitive to higher concentrations of glucose. Other questions on that? Again, we have to think about the different roles that the muscle and the liver are playing. Okay. Okay, so we said that glucose 6-phosphate's inhibition of hexokinase 1, like in organs like the muscle, is allosteric. Okay. All right. Okay, so then 3, the function of the liver in humans is to maintain the glucose concentrations circulating in the bloodstream at reasonably constant levels. This is so organs like the brain that use primarily glucose as a carbon source to produce energy via ATP have a steady supply of glucose. Okay, so again, remember the liver's thinking about all the other organs. It wants to make sure they have enough glucose for their energy demands. Okay. It also ensures that the levels of glucose in the bloodstream do not get too high. Okay, once glucose gets too high in the blood, that can cause a lot of damage. And so liver's also going to say, hey, there's too much in there. I better take it up and store it away as glycogen. Okay. All right, so using these plots to discuss why it makes sense that glucokinase in the liver would behave differently than hexokinase in other cells. So do you guys understand what's going on there? We got hexokinase in the liver behaving differently than hexokinase in our other cells, like the muscle. Okay, why is that?
What's it, stay in the cell?
Yeah, because what's the role of the liver? To lower the glucose if it's too high, or raise it up if it's too low. Right? It wants to help maintain that homeostasis, about 5 millimolar blood glucose levels. Okay. What's your role of your muscle or your brain?
Everything,
What?
like everything.
Everything. But they're not worried about the blood glucose, okay? Right? They're just like for your muscles, for instance, and that's easier to think about than the brain. Like your muscles are responsible for your movement, right? And so it needs energy to do that. Again, we said ATP is our body's form of energy. And how do we make ATP? The only pathway we've seen so far is glycolysis, okay? Is this right here. So your muscle is just taking that glucose and running through glycolysis to form ATP for movement. If you're moving, right? If you're not moving, well then your muscles don't have that demand. Okay? But it's not worried about how much glucose is in the blood. It has no way to know that. It just knows if it needs glucose or not, and if it needs it, it's going to take it. Okay. Discuss why the inhibition of hexokinase, so hexokinase 1 by glucose 6-phosphate makes sense. Okay. Sometimes I feel like it's repeating ourselves, right? But here's glucose 6-phosphate. If this comes back and inhibits hexokinase, why does that make sense? And again, remember, this is only hexokinase 1 that doesn't happen in the liver form of the enzyme. There's no demand for energy, right? That's telling you if this glucose 6-phosphate is building up, there must be no demand. I must be sitting on my couch eating some ice cream or something. Okay, my muscles are not moving. I got the supply of glucose, but there's no demand for energy, so it's not pulling that glucose 6-phosphate through. Right? It's not pulling it through glycolysis to make ATP. So it starts building up. And it says, you know what? It's like a negative feedback inhibition. Hexokinase, you don't need to be working right now. There's no demand for energy in this cell at this moment. If there was, there would be no buildup of glucose 6-phosphate. Okay. However, in the liver, we said this doesn't happen. I'll make sure I'm not getting any. Right? In the liver, it does not get inhibited by that glucose 6-phosphate. That's pretty amazing. Okay, it does not. Why? Because again, the liver is not the muscle, right? The liver is like, holy moly, they're just sitting on the couch eating all this ice cream. There's a bunch of glucose in the blood. I need to get it out. Else it's gonna wreak havoc in other places. Okay. So it just takes that glucose and makes a bunch of glucose 6-phosphate. And it can keep going and keep going, even if there's a buildup of glucose 6-phosphate, because that's the role of the liver. Get the glucose out of the blood if it's too high. If it's too high. Yeah.
So when the liver is like, oh no, too much sugar, take it out of the blood, it's now going back into cells, which is also going to help with that negative feedback loop, or is there a complete?
What do you mean it's going into cells?
So, like, I understand that when we're talking about the hexokinase in cells, and then we're talking about it separately in liver, there'd just be another one with the liver, when it takes all that sugar out of the blood, it's not like dispersing it elsewhere, because I remember you saying it's holding it in.
We're gonna see what it's gonna do. So part of it will be it'll start making glycogen. Okay, and part of it then if that builds up, then it's gonna start making fat. And so then we'll see build up of glycogen and build up of fat. Okay. Other questions? Okay, it says hexokinase is also inhibited by ATP, which is technically a substrate for this enzyme, right? Hexokinase takes this ATP and glucose and makes glucose 6-phosphate. ATP and glucose are the reactants. Glucose 6-phosphate is a product. But ATP can inhibit hexokinase. They can come back and inhibit it. Okay, interesting, eh? Why does that make sense?
It makes sense, but like, if there's no demand, we still have ATP to burn if we need it.
It makes sense that there's no demand. What do you mean by no demand?
Like, you're just sitting on the couch or not exercising.
You're just sitting on the couch.
You need ATP.
And again, another way I hope you guys start thinking about this too is when you hear the enzyme name hexokinase, what pathway comes to mind? Glycolysis. Okay, hopefully you're making that connection. You hear hexokinase, PFK1 or phosphofructokinase 1, pyruvate kinase, those three. You hear any of those three, and you're thinking glycolysis. And then the next train of thought is, okay, what's the product of glycolysis? ATP is a really important product of glycolysis. It's an energy producing pathway, energy yielding pathway. Okay. So if there's a buildup of ATP, because now there's enough to come back and inhibit hexokinase, that tells us there's not a demand for ATP. Again, we're just sitting on, we're like, well, there's not a huge demand for energy. And we're sitting on the couch and nice. Okay? And and so there's not a demand, ATP starts to build up, and it comes back, and again, it's just a way for your body to be efficient, right? Like, hey, hexokinase, you don't need to do anything because there's not a demand for energy right now. Like, I'm not burning up my ATP. I don't need to be going through glycolysis. Okay. In the muscles. Okay, so what features of an isozyme permit one isoform to be inhibited and another not to be inhibited, right? This can be kind of confusing. Like, they both are called hexokinase. How come one is getting inhibited by glucose 6-phosphate and another one's not?
Sites.
What do you mean by that?
Like, not necessarily active sites, but there's sites that allow inhibitory things to attach to it.
right, so there's different sites, right? So there might be a different allosteric site where something can inhibit it or attach to it, right? And so again, so the isozymes, remember, they catalyze the same reaction, but they might have a couple different amino acids that make up their amino acid sequence that allow for these different, right? One might have, so you can guess that hexokinase 1 has a binding site for glucose 6-phosphate to inhibit it. Where hexokinase 4, also known as glucokinase, does not have that regulatory site present on the enzyme surface. Okay, they both catalyze the same reaction. Okay, taking glucose and phosphorylating it to glucose 6-phosphate, but one has that binding site for glucose 6-phosphate and one doesn't. Again, just because it comes down to there's probably some amino acid sequence changes in there.
I'm curious. So the amino acid sequence for these enzymes is actually different. It's not just like allosteric regulation that is making them different.
Well, remember, allosteric regulation means that you have this place for the small molecule to bind other than the active site. So one of the isoforms has that binding site and one doesn't. And the way you would get that is you would have a difference, slight difference in your amino acid sequence. So they probably have very similar amino acid sequence for the active site, right, for the reaction. But then somewhere else along the amino acid sequence, there's some differences that allow for the formation of this binding site for this allosteric regulation. Okay. Okay, I'll put the key up to that later, okay, but make sure you do submit those group activities on Canvas. Okay. I want to continue looking at this regulation. Okay, so again, we look at step 1, hexokinase, and how it can be regulated differently in the muscle versus the liver. Yeah. Okay. Want to make sure I tell you that. Okay. Okay. So then the next enzyme we're going to look at is PFK1. Remember, it's phosphofructokinase 1. Okay. So again, this is a like a cartoon representation of the enzyme. Okay, you can see the enzyme in this white, blue, and gray are making up the different subunits of PFK1. Okay. It's telling you, remember, PFK1, phosphofructokinase 1, remember, is this reaction here. Here's PFK1. It takes the fructose 6-phosphate and ATP, those are the reactants, right? And makes fructose 1,6-bisphosphate and technically ADP. Those are the products. Okay, so this is the reaction that PFK1 catalyzes. Okay, so if we go back and look at that picture, we can see here that here's fructose 1,6-bisphosphate in yellow. Remember, that's the product of this. Okay, remember, ADP is also a product. Okay, so those are active sites, right? They just made the products. Okay, so again, in yellow, we have our fructose 1,6-bisphosphate, and red is this ADP. Notice there's these other sites out here, these allosteric regulators. It's a different site. It's different from this active site, right? Where ATP combined. Okay. So again, this is a major point of regulation in glycolysis. So PFK1 has many regulatory sites in addition to the active site. Okay. So remember, ATP was a substrate, it's a reactant, okay, in this reaction. But remember, PFK1 is in the glycolysis pathway. So ATP is also a product of that pathway. It's produced in glycolysis. So again, just like with hexokinase, if ATP concentrations get too high, okay, it can bind at these allosteric sites, okay, and it can lower PFK1 activity by lowering the affinity of PFK1 for the substrate fructose 6-phosphate. Remember, I took that fructose 6-phosphate and phosphorylated. Okay, so if we look at again substrate concentration versus enzyme activity, now we're looking at a different enzyme now. Okay, it looks a little different. Okay. So again, we're looking at PFK1, phosphofructokinase 1. That's the enzyme. This is its substrate, fructose 6-phosphate. Okay. Low ATP, meaning it's pretty active. It has this hyperbolic shape. Okay. Remember, we say PFK1, it's glycolysis. Okay. In red, though, we see what the activity looks like in response to high ATP. Okay, and again, if there's a lot of ATP around, then that PFK1 doesn't need to be working as hard. Okay, so it has a more sigmoidal shape in red. And again, what I have found the most useful is I think, okay, PFK1, glycolysis. ATP is produced in glycolysis. There's a lot of ATP around, that means the enzymes in that pathway can slow down. Okay. Okay. So it actually has a lot more anthracite than is even shown here. And a lot of things can affect the activity of PFK1. Okay, so again, it's showing you we have fructose 6-phosphate going to fructose 1,6-bisphosphate, right? Catalyzed by this enzyme PFK1. And if you notice, we said ATP inhibits, okay? ADP and AMP activated, right? And these are both signals that we're using up our ATP. Okay, ADP and AMP means we have hydrolyzed our ATP, right? We went from a triphosphate to a diphosphate or monophosphate. We've used that phosphate group. Okay. Citrate also inhibits. It doesn't make sense quite yet, but citrate is a sign that the cell is meeting its energy needs. So any energy yielding pathways seem to get inhibited. Okay. Okay, so you guys notice going this direction is our process through glycolysis. Okay, going the other way, if we take our fructose 1,6-bisphosphate and we remove the phosphate group and we end up with fructose 6-phosphate, we can go to gluconeogenesis. And remember, the opposing enzyme on that side was FBPase1, fructobisphosphatase. It's a phosphatase. Remember, phosphatases remove phosphate groups. Okay, FBPase1. So remember, FBPase1 is the enzyme that catalyzes the reverse reaction of PFK1. Okay, and so when you see this enzyme name FBPase1, again, my hope is that you're thinking gluconeogenesis. Oh yeah, that's an enzyme in gluconeogenesis. Okay. Hi, Carla. Okay. So something like AMP, look at AMP's effect, right? It activates this one. You should be able to figure out that it would inhibit the opposing pathway. Okay, that should make sense. Remember, we talked about we don't want a futile cycle, right? We don't want it going on and on and on. So if it activates PFK1, then it should inhibit the opposing enzyme. Reciprocal regulation. That's what they call reciprocal regulation. Okay. And again, the thought process here is that AMP. Okay. AMP is a sign that I'm burning through my ATP. Like I'm running. Okay. I'm using up my ATP. So I need to activate enzymes that are part of pathways that produce ATP, like PFK1, because that's in glycolysis. Glycolysis produces ATP. And I need to inhibit enzymes that are part of pathways that demand energy. Remember we said gluconeogenesis was very expensive. We don't produce ATP in that process. We use up ATP and we get glucose. That's what we get, which is important. Okay. But that's the thought process here. That's important. Thank you. One try.
Yeah.
I don't know who that was. Yeah. Hi. Okay. Questions on that? Yeah,
Is there a more kind of stronger effect if you promote one pathway and inhibit the other pathway versus just promoting one pathway? Because I noticed that AMP promotes glycolysis but inhibits gluconeogenesis, but ADP only promotes
yeah,
glycolysis.
I don't know. Like, is there more of effect because again, it's having like double activation here?
Yeah, I was just wondering, like, is there a difference between just reciprocal regulation, like AMP where it promotes glycolysis but inhibits gluconeogenesis, but ADP just only promotes glycolysis? Like, does AMP have a stronger kind of effect to start glycolysis versus ADP? I don't know if that makes sense.
Yeah, well, if we go back to this idea that AMP, remember at the very, we talked about AMP, the presence of AMP in our body leads to a whole like enzyme cascade. So it is a pretty powerful inhibitor and activator because it leads to right, if you have high AMP, it leads to activation of AMPK, which is a kinase. And that will go through and phosphorylate a bunch of things. And notice that if you have AMPK activated, then it is inhibiting things like making fats, which takes a lot of energy. So it's inhibiting that process. Again, it's inhibiting fatty acid synthesis in the liver and in your fat tissues. But it's activating things like telling your brain to eat more food because I need more energy, okay? Or burn fats, fatty acid oxidation, okay, because we need that energy for whatever, you know, for that, there's a demand for energy if AMPK is activated. So I think there's a whole system of like enzyme cascade that's going on that I know less about, okay, compared to like ADP. But ADP is another signal that ATP is being burned. Okay. But yeah, that's why I think AMP goes both ways. Sharon. Other questions on this? Okay. Oh, this is explaining why citrate is telling why citrate is a sign that your body is meeting its energy needs. Okay, so again, we looked at taking pyruvate, that's coming from glycolysis. Where we go next is pyruvate is made into acetyl-CoA. And then acetyl-CoA feeds into the citric acid cycle. Okay. This is all a way to produce energy. Okay. So citrate is starting to build up. That's their first product of the citric acid cycle. If it's building up, that means there's not a demand for energy. And that's why something like citrate would come back and inhibit PFK1. Because it's saying if citrate's building up, that means there's not a demand for energy. Okay, it's like ATP building up here. And that'll come up again. Don't worry about that too much. Okay. Okay, now there's this crazy regulation of PFK1, okay, by this molecule, okay? This molecule, fructose 2,6-bis-phosphate. Okay, I hope you guys have been reading and exposing yourself to the material, okay? Because, right, just to be clear, they go back, right? Remember the product, this reaction, is fructose 1,6-bis-phosphate. So there's a phosphate at carbon 1 and carbon 6, the product that we see in glycolysis, okay? But we're saying that this enzyme that regulates this reaction is regulated by this other small molecule, fructose 2,6-bis-phosphate, okay? Okay. So notice there's carbon 1, right? 1, 2, 3, 4, 5, 6. So carbon 2 and 6 have the phosphate groups attached. Okay, so this is not a glycolysis intermediate. Okay, this is only a regulator. And it's produced specifically to regulate glycolysis and gluconeogenesis. Okay. this small molecule, it activates phosphofructokinase 1, which is an enzyme in glycolysis, and it inhibits fructose 1,6 bisphosphatase. That's that FBPase1, okay, in gluconeogenesis. So again, we kind of looked at this before. We're looking at an enzyme activity versus substrate. PFK1 here, it's substrate fructose 6-phosphate. Without that small molecule, without this guy present, PFK1 is inactive at relative, at relevant concentrations of its substrate. Okay, so look at that. It is like really inactive in the absence of that small molecule fructose 2,6 bisphosphate. However, in the presence of fructose 2,6 bisphosphate, we can see there's a huge jump. It is necessary for the activity of PFK1. Okay, and I want to be clear that this is in the liver. Okay. So fructose 2,6 bisphosphate binds to PFK1 and it increases its affinity for the substrate fructose 6-phosphate. At the same time, fructose 2,6 bisphosphate can reduce PFK1's affinity for ATP and citrate. So it reduces affinity for the things that inhibit it. Okay. So again, PFK1 requires fructose 2,6 bisphosphate in the cell for any relevant activity. Okay. Now, what do you think? What do you think the effect of fructose 2,6 bisphosphate is on FBPase1? Right, so like write something down or commit to something in your head. How does this small molecule fructose 2,6 bisphosphate looks like this? Okay, how's that going to affect FBPase1? And again, if you forgot what FBPase1, remember it's the opposing enzyme here. FBPase1 takes fructose 1,6 bisphosphate and makes fructose 6-phosphate.
It's gonna activate it because the product is fructose 1,6 bisphosphate, right?
So do you see fructose 2,6 bisphosphate activated PFK1? Can you see that here? Yeah, does that maybe you're like, no, I don't see it on this graph. Okay. Remember, this is enzyme activity. So if fructose 2,6 bisphosphate is activating PFK1, what do you think it does to FBPase1? Yeah, Cleo.
It would inhibit because of that reciprocal regulation.
Yeah, reciprocal regulation, right? PFK1's glycolysis. FBPase1 is gluconeogenesis. Those are opposing pathways. We've got to reciprocally regulate them. If fructose 2,6 bisphosphate is activating this one, it better inhibit FBPase. Okay, so again, this is the enzyme versus substrate concentration for FBPase1. Different enzyme, different substrate. I mean, I know it's just a 1 and then a 6, right? There's a difference. Okay. But look what happens. Red is when fructose 2,6 bisphosphate is present. Okay, way activated here and inhibited here. Okay, and then look at that activity of FBPase1 and fructose 2,6 bisphosphate is absent, super active. Okay, where here it was super not active, super inhibited. So do you see that reciprocal regulation by the small molecule? The plot thickens. So if you have questions on this, let me know, because it gets even more interesting. What produces fructose? That's a great question. That's where we're going next. Before we go there, can you guys look at this and like, okay, yeah, that makes sense? Or is there, yeah, so like
For the FBPase1 activity, this is also in just the liver cell.
yes. Yeah. Other question? Okay. Okay, so where does that fructose 2,6 bisphosphate come from? Okay, so fructose 2,6 bisphosphate comes from the phosphorylation of fructose 6-phosphate, which was also a substrate in glycolysis. Okay, that was the substrate for PFK1. Here it is the substrate for PFK2. Oh, man. Okay, phosphofructokinase 2. Okay, so now here, and again, notice we need ATP. It takes a phosphate group from ATP and adds it to carbon 2 instead of carbon 1. Okay. So we got PFK2 that takes our fructose 6-phosphate, makes that fructose 2,6-bisphosphate. Okay. And then if we get rid of this, remember how important that was, right? In the absence, if it's not there, then this PFK1's not active and FBPase1's very active. Okay. So FBPase is fructose bisphosphatase. A phosphatase removes the phosphate group. So it's removing that phosphate group on the second carbon and you get back to fructose 6-phosphate. Okay. And the plot thickens some more. So do you have questions on this? It just gets more and more exciting. And the point is, and you guys, my comfort here is that you do not have to memorize this. Okay, maybe you start there, but you can reason this out later. Okay, let's continue to look at this. Okay. The interesting thing about this enzyme, right, this PFK2 and this FBPase2, is that it is one protein. It's one enzyme, but it has two separate enzymatic functions. I know that sounds crazy, right? So this PFK2 and this FBPase2 is part of one enzyme, but they're part of the same protein. And so, but they can do two, right? You can either add a phosphate group or take off a phosphate group. Now, depending on these hormonal signals, one or the other is going to be activated. Okay. So it's regulated by insulin and glucagon. Okay. Let's see what happens. In the presence of insulin, we activate another enzyme called phosphoprotein phosphatase. Okay. Notice that when the protein is phosphorylated, then the FBPase activity is active. The activity that removes that phosphate group. Okay. In the absence of that phosphate group, notice it's here and it's not here, right? When that's the phosphate group is removed, then our kinase activity, our phosphofructokinase 2 is active. And remember, a kinase, the kinase here, PFK2, adds a phosphate group to make that fructose 2,6-bisphosphate. Stick with me. Stick with me. Okay, so in the presence of insulin, we activate this phosphatase, it removes that phosphate group, thus leading to PFK2 being active. Okay. In the presence of glucagon, remember these are the hormones, presence of glucagon, this CAMP-dependent protein kinase is activated. So it's a kinase, it puts a phosphate group back on and has that FBPase activity is active. Okay. So what does that mean? Okay, let's see if we can reason this out. What does glucagon tell us? What does that hormonal signal tell in the body? Huh? Hunger. Why would what else? What does it tell us about our glucose levels? Glucagon. Low, right? Glucose is gone if we're getting a hormonal signal of glucagon. Okay. So if glucose is gone, what pathway should my body be doing?
Oh. Gluconeogenesis.
Gluconeogenesis, right? Glucagon. Glucose is gone. So what do you think your body needs? Your brain's like, I need glucose. Okay, liver's like, oh my God, glucagon. Glucose is gone. I gotta make some glucose. Okay. So I gotta go through gluconeogenesis. Okay, so let's see what happens. Okay, glucagon activates this kinase, activates FBPase2. Okay, if FBPase2 is active, right? FBPase2 is active. That means we're taking that fructose 2,6-bisphosphate and we're removing a phosphate group. We're getting rid of this. Okay, if this is active, we're getting rid of this, and we just end up with fructose 6-phosphate. Okay, so we go back to here. That means there's no fructose 2,6, well, there's less fructose 2,6 bisphosphate. Okay, because we activate that FBPase2, it's removing a phosphate group. And so we are like here, right? We have less fructose 2,6 bisphosphate. And that leads to FBPase1 being very active. And PFK1 being very inactive. Which, if I have a glucagon signal, is a good thing. Because FBPase1 is part of my gluconeogenesis pathway. PFK1, remember, that's part of my glycolysis pathway. That's a pathway that consumes glucose. And if my glucose is gone, that's not really what I want to be doing right now. At least in the liver, right? The muscle, you're running a marathon, well, muscles are still moving, even if you haven't eaten for 2 hours, right? It's still gonna suck up glucose and do glycolysis, but the liver's like, oh my God, the muscle really needs some glucose, so I need some gluconeogenesis. I better activate that FBPase1 and inhibit PFK1. Let's go back and look at insulin, okay? Here. Now, insulin, what is that hormonal signal tell my body? There's there's enough, or there's glucose levels in the blood are getting high. Okay. Means we're raising up our glucose levels. So if our glucose levels are getting high, then what's the liver thinking? What's it got to do? Glycolysis. I got to do the pathway that consumes glucose. Okay, I got to consume it. Okay. So let's see. In response to insulin, this phosphatase is activated, removes that phosphate group, therefore activating PFK2 activity. PFK2, right, is phosphofructokinase 2. It's a kinase. It takes fructose 6 phosphate, phosphorylates it to this fructose 2,6 bisphosphate. That's that small molecule, right? That's this guy. Okay, making this guy. So PFK2 is activated. It makes this. So now we have a lot of fructose 2,6 bisphosphate around. Okay, so what does that look like? In the presence, right? We activate PFK1 and we inhibit FBPase1. And again, we can reason that out, right? PFK1 is part of glycolysis. FBPase1 is part of gluconeogenesis. In response to an insulin signal that's telling my body there's too much glucose, I better pick up my glycolysis activity by activating an enzyme that is part of glycolysis. Questions on that? Lots. So there's this whole, I don't think here we go. Well. I think it's at the very end of this slide. Okay, right, there's this whole enzyme cascade that happens, right, in response to a hormonal signal. Okay, so you can see in our case, like glucagon activated the kinase, right? Glucagon activated the kinase, which activated this phosphatase, which led to the getting rid of the fructose 2,6 bisphosphate, which led to increase in FBPase1 activity and decrease in PFK1 activity. Okay. So there's this whole kind of cascade effect due to the glucagon signal. Okay. So questions about that? So I'm not so much interested that you memorize like, oh, this is phosphorylated, this is active, and this is not, or this the names of here. It's more like insulin is telling my body there's too much glucose, so I better lead to activation of glycolysis enzymes. So you gotta be able to associate PFK1 with glycolysis. Glucagon is saying glucose is gone, so I better be activating gluconeogenesis and inhibiting glycolysis. Okay. At least in the liver that is concerned with our blood glucose levels. So that's PFK1 regulation. Okay. The last enzyme that we talked about in our steps of regulation, right? 1 and 3, and then 10, which is pyruvate kinase. Okay. So pyruvate kinase is our step 10 of glycolysis. Okay, remember it takes PEP, that phosphoenolpyruvate, and gives us pyruvate. So it removes the phosphate group. Pyruvate kinase itself, the enzyme itself, okay, when it's phosphorylated, it's inactive. Okay. If it's dephosphorylated, then it's more active. Okay. So again, same thing, a phosphatase removes a phosphate group, and a protein kinase a kinase adds. Okay, now let's see if we can make sense of this. Again, in the liver only, we get a glucagon signal. What does that tell us? We need gluconeogenesis, right? Glucagon, glucose is gone. And again, notice that says liver. Liver's like, oh my God, glucose is gone. Like Jacob said, we need glucose. So what pathway should we be activating? Gluconeogenesis. Now, what pathway is pyruvate kinase part of? Glycolysis. So in response to glucagon, do we want it active or do we want it inactive or inhibited? We want it inhibited, okay? So again, glucagon leads to this kinase being activated, which leads to phosphorylation of pyruvate kinase, which inactivates it. Okay, so you can start to see how you can reason these out. Okay, in response to this signal, what is that telling the body? Where am I in the body? What am I doing? Right? If I'm the liver and I'm concerned about blood glucose, then should I, what pathway do I need to go through? Okay, what's going on over here? Okay, so we have pyruvate kinase. So this is the steps, right? This is glycolysis steps. So fructose 1,6 bisphosphate, going through 6 more steps to get to PEP, phosphoenolpyruvate, and this is the last step of glycolysis, making pyruvate. So we make ATP in that step, and it's saying that ATP, acetyl-CoA, and long-chain fatty acids, these are all signs that the body is meeting its energy demands, right? If there's ATP around, then that means we're not using it up. And it comes back and it inhibits pyruvate kinase. Can you reason that out, that ATP would inhibit pyruvate kinase? Can you reason that out?
Yeah, it's the same reason it didn't activate kinase. Needs to be stored when we're not doing anything.
If we're not, right, if there's a buildup of ATP, that means we're not burning through it, right? We're not burning through it. So yeah, it comes back and it's going to inhibit enzymes that are part of a pathway that produce ATP. Okay, so remember, pyruvate kinase is an enzyme in glycolysis. Glycolysis is a pathway that produces ATP. But if we got ATP lying around because we're not using it, then the ATP is going to come back and say, hey, pyruvate kinase, you don't got to work so hard. Kick back, okay? Fructose 1,6 bisphosphate activates it. Again, it's kind of like, it's like a preview, like it's like letting you know we're coming down the chain, right? So get ready. It activates pyruvate kinase. Okay, and then we'll learn more about pyruvate and alanine when we start talking about amino acids. Okay. Questions for me? Yeah.
I was wondering for hexokinase, phosphatidylkinase 1 and pyruvic kinase, are they also all transcriptionally regulated?
Yeah, so that's what the last couple slides are here. So remember, we talked about transcriptional, there's just levels of regulation that can be on a transcriptional level and a translational level, and we don't talk about them as much, but yes, thank you for bringing it up, because I do want to remind you that there is that level of regulation that doesn't come up so much in this class. We talked about it briefly when we first started talking about regulation, but yes, so we can change, right, the level of transcription of a lot of our genes. That's going to affect our different pathways. Remember, this is going to affect transcription is when we take our DNA and go to RNA, and then translation, we take our RNA and go to protein. So you can imagine the more protein we have present, the more enzymes we have present, they can process more substrate. Okay, the less enzymes present, they can process less. One of the other things that happens, right, is right, if there's insulin, then that says there's a lot of glucose, so we want to be doing glycolysis, so we can increase our transcription of hexokinase, PFK1, pyruvic kinase. We can upregulate those at a transcriptional level. So this is an example. You guys, this is more just to expose you guys. I don't test you on this stuff. Okay, but I just want you to be aware of it. Okay. So if you have glucose coming through, okay, and again, we have glucose getting phosphorylated to glucose 6-phosphate. Remember, through pentose phosphate pathway, we end up with this xylulose 5-phosphate, okay, and that can lead to activation to this phosphatase. This is a transcriptional factor, okay, and so it gets dephosphorylated. It can enter into the nucleus, okay, and in the nucleus, it can bind to a region on the DNA that's out before the part of the DNA that codes for the RNA, okay? So it can lead to more production of the mRNA, okay, through transcription. So the thing about transcriptional regulation is that it can get pretty complicated. So I just put this slide up there so you can see that it's controlled by many different factors. Like these are all binding sites out before the gene, right? Here's where we're starting to make our mRNA, right? But it has all these different binding sites for different transcription factors, different proteins and different regulatory molecules that can bind before on the DNA and affect the transcription of the DNA to RNA, activating it or inhibiting it. It's a huge orchestra of regulation going on there. Okay. Questions about that? Yeah.
So in response to higher insulin, FOXO1 activates which transcription?
Yeah, let's look at that. So, okay, so FOXO1 activates transcription in response to insulin. So insulin binds outside the cell. Okay. And then we have phosphorylation. So here's FOXO1 in the cytosol. If it's phosphorylated, right, it's harder for it to pass the membrane. You have to remember, phosphate group is highly charged. Membranes tend to be made of, have these hydrophobic centers. So if it gets dephosphorylated, then it can enter the cell. So let's see. I'm sorry, the nucleus. Thank you. And then here it's showing you that it's linked to upregulation of the mRNA of glucose 6-phosphatase and PEP carboxykinase. So remember, these are both these are both in gluconeogenesis. Okay, so FOXO1 upregulates transcription of these enzymes. But when insulin binds, right, it leads to activation of this kinase, protein kinase B. So it will phosphorylate FOXO, so it cannot enter. Because if we have insulin, we don't want to be activating gluconeogenesis, right? Insulin is saying plenty of glucose in the blood. You would not want to do gluconeogenesis. So normally this would be doing gluconeogenesis, but in response to insulin, phosphorylates that transcription factor, it cannot enter the nucleus, and instead it gets tagged for degradation, which is good in response to insulin. You can always reason it out in response to hormones. Okay, all right, you guys, so you guys work on, we'll get some time on Wednesday to work on activity 27. I'll change the due date of that one, in the notebook, but take a look at it. And again, I'll give you some time in class, but to really appreciate the knowledge in there, take a look at it on your own as well. Right, so we'll look at that and we'll start looking at glycogen on, Wednesday.
Like.